Welcome to the third lecture in the FJelinekSeries of lectures, to which we invite prominent scholars from abroad to present a talk on the subject of their choice or preference. And I am very happy that I have the opportunity to welcome Professor Dan Flickinger with us. You could have found on our website all the attributes of his work and personality. I just want to mention that he is coming from Stanford University, and if I'm not mistaken, that this month he is in Saarbrücken, not too far from us. So that we use the opportunity to have him with us here in Prague today. Dan is well known, among other things, as a specialist in HPSG, and recently, or not that recently, interested in tree banking and using this formal framework in tree banking of English. So I think that we will be very happy to listen to his talk on the combination or possible combination of symbolic and statistical methods in corpus-based natural language processing. I have just to add one personal remark. I'm very sorry, but I can be here only during your lecture. I have to leave right after the lecture, and I will pass over the discussion period to Jan. So please take the floor.
Thank you. Thank you for the invitation to come talk to you about work that I have been doing with a number of colleagues scattered around the planet. Very few of them remain at CSLI, which is why I have to get on airplanes to travel to do my continuing collaboration. Currently I'm enjoying a nice day in Saarbrücken with short trips to Oslo and Sofia tucked in between. I enjoy Saarbrücken, really. I like to stay there. Today I would like to talk to you about combining symbolic methods, that is, linguistic grammar-based methods, with statistical methods, and in particular, methods used for parse selection or parse ranking. There are, of course, a variety of other symbolic methods I won't talk about today, and a number of other ways you could use statistical methods. Maybe you can suggest some good ideas when we finish the lecture part to move beyond the current use we're making of these statistical methods. We describe somewhat arrogantly the kind of approach that we take, which is grounded in linguistics, as deep NLP. This is maybe promotional work and not so easily defensible in contrast with many of the statistical methods, which are also relatively deep. This is, I think, a matter of degree, not a difference in kind. But we are interested in concerns that involve robustness and accuracy and efficiency, and then crucially also ambiguity resolution. That is, as a linguistically grounded approach, the grammars we build attempt to describe all of the possible structures that a given string might have associated with it, not just the one intended string. The grammar is essentially describing the space of possible analyses, possible interpretations, and then something else must make the difficult choice among those candidate interpretations. I'll give you a couple of examples to remind you of this pervasive burden of ambiguity resolution, which machines have to do without very much help, and which we can do more or less effortlessly as humans, luckily. Otherwise, language wouldn't work very well for us. So the fifth on here is just kind of showing off. We have an implementation and have decided on a framework which is at its heart reversible. That is, the description of the grammar is declarative, neutral with respect to whether you are mapping from form, that is the surface string, or the sounds, to meaning, or going the other direction, taking a meaning representation and constructing the output string. The grammar doesn't care which of those two directions you're trying to implement, the software, of course, has to care a lot, and it is a challenge to build an efficient engine which can do parsing, and potentially a somewhat different but related challenge to build an efficient generator. But even there, the implementation of these algorithms is essentially the same. We generate by parsing, so at its heart, there is a parser always at work building candidate analyses. When you're looking at a string, it's building phrases kind of obviously built up of the words, the tokens that you see. When it's trying to generate, it's taking bits of meaning representation and constructing possible phrases, possible substructures, which would be relevant for the structure for the overall sentence. You can maybe quickly see that could be a problem for efficiency. I won't say very much about generation today, although it comes up in the first of the three examples that I want to talk to you about. But I provide you with this picture of the 5 gods that I must pay service to. I won't tell you which ones are which, but probably that reversibility guy just with his nose sticking above the surface is maybe the least important of those. The other 4 are stern and forbidding and pose a constant problem. They are also essentially at war with each other. That is, it is possible to build a more accurate grammar by making it less robust, or making it both accurate and robust, but rather less efficient. Providing something which can do all of these pieces in a relatively good combination is an ongoing challenge, I think, central in natural language processing that has linguistics somewhere in its core. I'm working for much of this work in the Linguistic Grammars Online laboratory at CSLI, which is directed by Ivan Sog, who has been at Stanford even longer than I have, which is an eternity. We have been collaborating since '94 on building computational resources, linguistic-based resources, as Eva said, framed within this head-driven phrase structure grammar, or HPSG framework. We have mostly focused on English. That's not surprising. We're in California. That's one of the languages spoken there, more or less. Spanish is also spoken. It's the other language I kind of speak. But we have excellent colleagues in Barcelona who speak a kind of funny version of Spanish. They call it real Spanish. And they are building resources. So in this case, we are collaborating across the water on that second language. English provides us with a good basis for exploring the general methodology, and then it's important to check the sanity of those methods and see how many of them can be ported across to other languages. So we're collaborating with industrial partners in a number of places. Most of the software comes from Saarbrücken, from the DFKI, which you may know about, from the Cambridge Computer Laboratory, and now from the University of Oslo. Those are our industrial software engines producing the software. They also teach classes, but I look to them as sources of improved software. And we're building grammars for a number of languages. I'll only talk about English today, as I said, but there are maybe another dozen reasonably well-developed grammars scattered around. Generators, parsers, development platforms, annotation tools. I'll say maybe most about those annotation tools because, as was indicated, we are very much interested these days in building tree banks, in building humanly annotated corpora, which can be used for a number of purposes, in part at least for ambiguity resolution. The grammar of the laboratory you can find at lingua.stanford.edu, and this consortium has the rather tortured name Delphin, which is a German word for dolphin, so we get a nice little picture of a mascot. But to make that turn into something was roughly Deep Linguistic Processing with HPSG Initiative, which is impossible to say, and probably not even grammatical. But Delphin you can remember, and the only annoying thing is you have to remember to put the little hyphen, the dash in, because somebody got to the name before us. Life on the internet. All right, your one slide on head-driven phrase structure grammar, and then you're free. You don't have to worry about this framework anymore and can go back to the real world. We view grammars as consisting of signs. Our task as linguists is to describe the nature, the variety of the signs, the linguistic signs that we encounter. Those can be either of the type word or of the type phrase. In fact, they can be of slightly more types than that, but let's keep it simple. We have, in this HPSG approach, we have a very lexicon-centric view of the world. Most of the linguistic information resides in that lexicon, and then the grammar consists of a relatively small number of rules. much bigger than Ivan, my colleague, would like, but relatively small. So in his view, every language should have about 7, although maybe he's pushed it up to 10 or 15 now. We, in the English grammar, have around 200 grammar rules. That's to describe many of the relatively unusual or specific constructions, and also to differentiate among, say, 50 different kinds of coordination structures, verb phrases, noun phrases, adjective phrases. There are places where we have put some steroids into the grammar and it has expanded in certain local regions, but it is still the case that almost all of the information is lexical. We organize the verb hierarchy into subtypes and the noun hierarchy and the adjective hierarchy. That use of types and the features with attributes and values that we assign to those types is how we express generalizations. Both the real generalizations that hold pretty much across the language and even the idiosyncratic information, which of course everyone agrees should be in the lexicon. Lately we have been expanding our use of constructions. That is, as I said, rather growing this inventory of syntactic structures that seems in many cases a better place to explain a construction, a phrase type, a grouping of words that shows up with regularity, rather than trying to maintain a very purist view that everything should be in the lexicon. The hope is that gives us a more linguistically satisfying description. And I've already bragged about our parsing and generation, though I won't show you much of that today. Okay, so we have type feature structures. I'll show you, I think, maybe not even one single example of those today. I can't quite remember. I may have taken that slide out. They are essentially clusters of attributes and values, and if you take the simple version, you might agree that a noun like dog and a noun like dogs, these two lexical entries on their surface forms, have to be pretty much the same thing. But we want to distinguish one from the other because one is singular, one is plural. They will have agreement properties, say when they are the subject of a sentence. They will correspond to an appropriate morphology on the verb. So the grammar must care about that contrast between singular and plural. We describe that in this simple case as a noun whose number value is singular. So that feature number and the attribute singular make up a pair. That's an attribute value pair. And we have a bunch of those. For nouns, we will also distinguish case and potentially gender, at least for pronouns. For verbs, we care about tense and auxiliary and various things. That all sounds reasonable, but then you look at our feature structures and it's all feature structures, which means that the description of a transitive verb may have 150 or 200 distinct attribute value properties that cluster together to describe that transitive verb different from every other kind of sign or object in the grammar. There are a few people who view this as an object of beauty, but we think we gain a good sense of, a good degree of generalization, of linguistic explanation from adopting that relatively noisy notation. Today I want to talk about 3 applications of this linguistically grounded approach to NLP, to processing, where in each of these 3 cases we have moved to combine substantial amounts of statistical processing as a part of the solution, as a part of solving the larger problem. Machine translation is perhaps the most boring but the most enduring one. Every other application, information extraction, grammar checking, everything else will come and go with the waves, but humans insist on talking different languages and we need to communicate between those two, and hence I believe we will always have machine translation as one of the applications we work on in NLP. So I want to talk to you about one of the 2 experiences, extended experiences, that I and colleagues have had in that particular branch, but I won't spend too much time on that because I'm much more interested in our current work, which is involved in information extraction on the English Wikipedia and on grammar checking for small children who can't object. Okay, so in machine translation, there are the current, let's call them winners. That is, the people who do it really well, using statistical methods. Google is surely the biggest player in this game, both in terms of size and success at this point. They take advantage of very large data sets, trillions of words of text, maybe billions of words of parallel corpora that have been translated and sentence aligned. Wherever they can get that kind of data, they can produce a reasonably interesting translation engine. They are exploiting nothing about linguistics in the sense of having written down rules of the grammar. They're starting to, according to rumor that we hear in Silicon Valley. But up until now, they have been quite aggressive about saying, If we find anyone who's had linguistic training in our staff, we relocate them or fire them. We don't want linguists. They just confuse things. They clutter up. They slow down the process. We can find enough information in the redundancy that's present in natural language, the repeated patterns that you can find just by looking at n-gram windows within the string. Admittedly, they can look at 5 grams or maybe even 6 grams, possibly even 7 in some cases, because they have so much data. So even with the sparsity of data, they can arrive at reasonably good methods. But this approach at some point has to break down. It cannot cover the long tail of constructions which are not local in the way that this approach assumes at a very deep level. So unbounded dependencies, anaphoric binding. There are a number of properties of language where the two pieces that are somehow importantly linked together don't appear within some limited n-gram window, and the core methods being used in this kind of translation approach just aren't going to work. Of course, they can get to 80 or 85%, let's say, with those methods. That's way better than anything else we can do at the moment. But we, in the project I want to describe on this logon project, decided we had no reason, in fact, no hope of competing with that kind of statistical approach, that we would come at it from the other direction, trying to see how much we could do with grammar-based approaches and find out where the obstacles emerged in that kind of approach, in that analytical approach. So the approach we have is built on handbuilt computers, but I have to concede we also use massive computing. Our methods are maybe more detailed, more accurate, but certainly not as efficient. So there's a cost to be paid someplace for this. In comparing or measuring what we are doing, we're interested in many of these same dimensions. We're interested in efficiency and robustness, the cost of development, which is different from the runtime efficiency, very different from that measure. And we're, of course, also interested in adaptability. Can the method we use work for the next language pair? Can we do something without having to start completely from scratch, as must be currently done with a statistical method? You need data from 2 languages with a statistical approach, and without that you can get nowhere. We are interested in how far we can get by having monolingual grammar development, and then some modest amount, some bounded amount of manual adaptation. And we're interested in what the improvement curve looks like. This is the one place in which we probably have an advantage over statistical approaches, even in the current method. And I'll talk about that in just a moment. The hand-built grammars, until maybe 5 or 10 years ago, looked like they were just hopeless for this kind of approach. In fact, there has been kind of a nuclear winter of grammar development over the last 10 or 15 years as these statistical methods have gained success. It's hard to find very many people at an ACL meeting, Association of Computational Linguistics, that will sit in a corner and say, what does your analysis of relative clauses look like this week? That's just not the kind of conversation we have looking at specific linguistic analyses. It's very much about machine learning methods and better tuning and different mixes of strategies, hybrid approaches. But in the meantime, quietly in the background, the theories have improved some, and our engineering techniques, the methods have improved some, and the machines have gotten a whole bunch faster. And so we're now able to see robustness in somewhere around the 90% range on each new data set we look at without any further manual tuning. It used to take years of adjustment to get to that kind of completeness. You can see there's still a gap there. We're still 10 to 15% away from having something to say about every sentence we see. And in particular, we're in trouble if the person who wrote the sentence made a mistake. We don't have very much robustness built into this kind of approach because we are trying to emphasize accuracy, a point of distinction from these more statistical methods. The speed is painful. It costs us 1 to 10 CPU seconds to get through an average sentence. The shorter ones are really fast. The longer ones are much, much longer. We will not sell this technology to Google when they have to process billions of sentences every week or every day. It would just cost too much. So this kind of efficiency cost limits to some extent the application domains that we want to work in, but we think there are still opportunities that are relevant even for doing sustained development. Importantly here, the accuracy level has gotten to about 80%. It's pretty easy to find parsers that will give you an analysis for every sentence you see. In fact, every string of words you throw at it. They will provide some hypothesis, but it is nowhere near correct in many, many cases. With this linguistically driven approach, we have gotten to the point where we can see about 4 out of 5 sentences receive a correct analysis. That's still ducking the problem of how I choose that analysis from the competing ones, also assigned by the grammar. But at least the grammar has an intelligent thing to say about 4 out of every 5 sentences. And we think there is good portability in this approach, both for new domains and in the case of machine translation for language pairs, although we don't have very powerful evidence to maintain that, support that optimism. But built into the approach we're taking seems to be some promise for portability. Now let me talk about this ambiguity, because that's kind of at the heart of the puzzles, for the 3 puzzles we're talking about today. Machines don't have any real common sense or real world knowledge. We simulate or model partial world knowledge in a machine with AI systems, with ontologies, with huge thesauri or gazetteers, sources of static information that describe some part of the world. But we don't have very good reasoning engines that are efficient and broad in scope even after many decades of work in artificial intelligence. That's just a really hard problem. Harder even than the natural language problem, apparently, at least right now. So our engines, being driven as these are by linguistic grammars, produce lots of candidate analyses. And we typically only want one. Applications, humans, pretty much everybody. Only linguists want more than one analysis for a given sentence. Consider this sentence, have a report on my desk by Friday. If you contemplate that sentence, you will in your mind come up with some picture of the state of affairs that this sentence describes. And I would suspect that it's a sentence chosen for this reason. You won't all have come up with exactly the same reason or the same picture. Here are, you probably know enough linguistics to answer this question, all of you anyway. How many of you think that report is a verb in that sentence? That is, that there is an act of reporting going on. One of you is brave enough to say so. All right. And the rest of you all thought it was a noun? Noun, yeah. Okay, many of you were abstaining. All right, fair enough. The variety of analyses could be summarized maybe in these 4 or 5 categories. Let's cause her to summarize the status of my desk. So tell her to come in and tell me whether I ordered this brand new lovely desk and it just hasn't showed up. I want that representative to show up and give me a report. When am I going to see my nice new beautiful desk? And she's got 4 days to do it because today's Monday. By Friday I need to know. Or maybe I want her to stand on my desk while she's giving a report about something. I don't care what. But whenever she reports, she should be standing on my desk. Not a friendly interpretation, but perfectly reasonable in terms of the literal meaning of the words in the sentence. She could also stand next to a poor guy whose name is Friday, Mr. Friday, and I want her to give the report while she's standing next to him. Of course, usually Friday is the name of a day of the week. But there is a famous story in English literature about a maroon sailor whose best man, his friend, his helpmate, is named Friday. Good man Friday. And so if we're talking in that space, then maybe more likely Mr. Friday shows up. And then there's also this rather strange but possible interpretation. I want you to take possession of that report. Have it. Like have a piece of cake or have a cookie. Take that report and somehow do that by Friday. Come into possession of that report by Friday. Maybe one of the less likely interpretations. And then, of course, there's a very plausible reading, which is cause that report which she wrote, that is, report as a noun, her as a determiner. Most of you seem to agree with that. Have that report, I don't know what its topic is about, but I want that report to show up on my desk, and I want it there by Friday. A typical order that shows up in most businesses. Those are relatively distinct readings, even to the point of choosing part of speech, basic part of speech for the lexical item, and they drive the machine in one direction or another. We need some way to make the choice about that causing sense of have and the noun sense of report and the location having to do with the causing event as opposed to the report topic, and Friday being temporally located as a constraint on that report. Those are tricky things to figure out. You would need a relatively large amount of domain knowledge in order to be able to get that from general purposes. We tried building those heuristics in domain by domain, application by application. I was part of a startup company once, and we spent ridiculous numbers of hours and money, not ours, somebody else's, trying to build heuristics in that would work for each new customer that came along using our natural language software. it was clearly brittle. There wasn't much of an underlying theory. We weren't ontology people or AI specialists. And it was almost impossible to maintain. The labor required, the skill was relatively high. The alternative approach didn't seem plausible in 1999 when we first started that game, but now seems the only possible correct answer. Namely, use statistical methods, get some training data, annotate all the wrong analyses plus the right one, give it to a machine, any good machine learning system, and have it figure out a model. And the more data you give it, probably the better the model will be. We tried that strategy, this hybrid strategy, in a logon project which involved translating from Norwegian to English. Not the most commercially relevant language pair you could pick for a project, but if you go to the richest country on the planet and they want to work on Norwegian, who's going to complain? So I worked on Norwegian. Or at least I worked on the English translation from Norwegian. My colleague Helge Duvik in Bergen was the builder of the Norwegian grammar. He was also working very heavily in a linguistic framework, but his focus was in lexical functional grammar. So he's using a slightly different framework, which we thought was a good exercise in inter-theory communication. This is a summary of where we got at the end of that 4-year project, which finished in 2007. We worked on 5,000 original Norwegian sentences in little brochures describing the beauties of the Norwegian landscape and hiking. And then the project paid 3 professional translators to make English translations of those. So we had 15,000 sentences in English, 5,000 in Norwegian, and the 3 in English for each Norwegian sentence were pretty similar, but almost never identical. It's easy to get slightly different paraphrases for each of those sentences. And then we tried translating those 5,000 sentences end to end, analyzing in Norwegian, running through this mysterious semantic transfer engine, which I'll say a little bit about, and then generating English from the meaning representation that came out of that transfer engine. So a relatively classical, deep approach to NLP, to machine translation, with a set of transfer rules that map between Norwegian and English. The Norwegian grammar in lexical functional grammar was already in existence before we started. It represents about 8 person-years of work, almost all Professor Duvik. The English grammar at that time was about 12 years of work, 12 person-years of work, mostly me. And then we added this maximum entropy engine to do both the parsing and the generation modeling, to do parse ranking to choose the right analysis, or when I generated a bunch of possible candidate strings to represent a meaning in English, we had to pick among those strings. A very similar problem, and a clever PhD student at the time, Erik Veldal, who's now a professor in Oslo as well, worked out a nice way of twisting and turning that standard approach to parse selection to work also for generation. And then we went back to the old bad old days of writing manual rules, but in this case there was a slightly more theoretical grounding to it. We have a set of transfer rules which involve some abstract types, mapping certain structures in Norwegian to certain structures in English, linguistically more informed, and then we of course took a bunch of them from a bilingual dictionary. If you only have 5,000 sentences to worry about for your training and test corpus, you can essentially exhaustively cover the vocabulary. That wasn't a major challenge for us. It just took a while. And then we were interested in how fluent, how correct and how fluent we could make the result. That coverage issue was an interesting point that goes back to that question about scalability, about what happens if you continue to work on a problem over time with more and more effort going into it. The shape of this approach that we take is essentially linear. That is, for every 100 hours of grad student time that we put into that project, or my time, or Elke Duvik's time, we got essentially a linear increase in improvement. That was rather surprising to us. We thought it would tail off at some point. But we're only about the 60% success rate here in successful end-to-end transfer. But at each point, up until the very end of the project, we could just keep on going. It was clear that we could add another bunch of rules, another change or tuning of the grammar, better aligning of the two grammars. We could make progress. That is not the shape of a curve if you're using machine learning techniques. Yeah.
All the training, the data set and the test data set different, so this is human access to the test set.
the machines always kept the test set, we always did a tenfold cross-validation, and then we had a withheld 10% that the humans never saw. This is also reflecting the 10% that we didn't see. What was interesting is we had two different test sets from two slightly different domains, and on one the machine did better than it did on the training data, and on the other slightly worse. So I think we are still suffering from too little data. There was a little noisiness or some noise still in the small scale of this measure. But we were attempting to be relatively careful, relatively sound about those measures. So I never got to see the test data during that 4 years of development. I could always just close my eyes and keep my fingers crossed and see what happened to that curve. But it continued its steady march upward. Of course, we thought we could just go to the Norwegian government in 2007 and say, look how great this is. Another 5 years and we'll be at 120%. Just give us more money. They didn't fall for it. They're rich but not dumb. So in terms of the success rate, you will not be surprised that for short sentences, short utterances, often just phrases, we did pretty well. So we got almost everything up to 5 words long successfully translated. I don't take great pride in that. It's just, it's a little tricky because you have less linguistic information in short utterances. Fewer cue words, fewer function words. So it can be somewhat challenging, but it's not that hard. In this range of 5 to 15 words, we were still doing pretty well, but starting to drop off, and you can see this kind of depressingly predictable curve. That as the sentences get longer, the chances of there being something in one of those sentences that we didn't yet accommodate correctly continue to rise. It's just the sheer tyranny of numbers here. That because we can fail in such easy ways on such simple missing phenomena within the grammar, there's a good chance of failure, and the longer the sentence, the more that failure chance arises. You can also see something here about the ambiguity, the number of possible translations we produced. Even at 10 or 15 word sentence, we're producing hundreds of candidate alternate analyses. They might only be different in the slight variation in the order of two adverbs, or the punctuation that distinguishes a sentence initial prepositional phrase from the rest of the sentence. So these are character by character distinct, these distinct analyses. They have something slightly different that's linguistically salient. And then up here at the top, we just didn't care. There was only one or two sentences. I think we can't learn anything from that. But the general shape up to 20 or 25 words, where we have substantial amounts of data, we could see that the ambiguity was going up pretty much the way we would fear. So in order to handle that ambiguity, we essentially broke it up into its three component problems. There is, of course, ambiguity in the analysis of the Norwegian, just like there was for that English sentence. Always more than one way to interpret it. Then there's ambiguity in the transfer grammar. That is, for a Norwegian semantic predicate, there might be 2 or 3 that are near approximates, and I don't know which one is the right one, so we propose all 3 of those. And then when I generate, I have various word order degrees of word order freedom. So in generation, there was also potential variation. So I have this threefold opportunity for expansion of possible ambiguities. And we built models, hand annotated models for each of those 3 components. A tree bank for Norwegian, essentially a tree bank of a kind for the semantic transfer, and one for English. And then we tried to figure out how to make those 3 work together nicely, and then we built a covering model for all 3 components that did essentially some final smoothing to see if we could make that as nice as possible. And here we made pretty heavy use of a strategy that's quite common in statistical NT, namely using a monolingual model with vast amounts of data as a kind of smoothing to say, have I ever seen that 7-word sequence or that 3-word sequence anywhere before in my entire history of knowing English? In the machine's case, they can see a lot of English. And so we use that smoothing to exclude those strings which we thought were locally sort of same, but produced sequences of words which occurred rarely or never out in the vast wild of English data. For this, we use the relatively modest British National Corpus, which is 100 million words. It's part of speech tagged. It's a little better tamed, rather more balanced than the wild web, but it still gave us a really measurable benefit in terms of accuracy. This ranking for the generation, the re-ranking at the end to produce the right strings, Eric, because he was doing a PhD thesis, did this carefully, did it right, wrote it up nicely, and it ended up being able to build a model which brought us to about 72%. He gained about a 2% improvement in exact match by using the BNC, this British National Corpus monolingual model, which said, up to this point you produced a sentence for me which is not exactly what a human would say, but if I apply this restriction to say, is it fluent? Is it something that locally, independent of the whole sentence, is it locally n-gram-wise fluent? I can get a 2% improvement, or Eric could get a 2% improvement. So in almost 3 out of 4 sentences, we're getting the same generated output that a human would have picked, that a human did pick out of the candidates. This is all within the space of what the grammar can produce. So the gold annotated data we were using to measure for the evaluation resulted from the human saying, okay machine, what do you think the possible generated outputs are for this particular Norwegian sentence? And then the human would pick the one which was the closest, the most natural, the most desirable equivalent. And in some cases the human said, these are all terrible. They would just reject those. So the machine has some negative data as well as positive data, which it also uses in the building of that model. Okay, so let me just show you a little bit of what we did near the end. This isn't the actual final story because we had an aggressive 6 months of polishing to get ready to show it off to the Norwegian funding agency, thinking they'd give us some more money. But before we did that final polishing, we got some translations that were pretty close to right. On the West Bank, 3 mountain pastures lay there almost besides each other. It's not exactly right. In English, you would say beside each other. Besides each other looks almost the same, but actually means in addition to each other. That besides doesn't mean the same thing as beside. That was a place where all of our fancy machinery up until the very end couldn't quite make that fine-grained distinction because the distribution of beside and besides syntactically is almost identical. Shows up with the same shapes in the same sentences next to each other with mere substitutions, minimal substitutions. So it took some rather heavy processing. That's where the BNC came in and saved us and said, you know, I just never see pastures and besides. Just doesn't show up that often. Or any of these other n-grams that are in that sentence. In this case, does anyone here actually speak Norwegian? That's lucky for me. I think it's the case that these are fair translations. I have given these three examples to Norwegians and they haven't screamed at me. They might have been laughing at the bar afterwards. If you don't want to go so far, Besteron Runhø is an excellent alternative. That seems a perfectly fine translation. Nothing funny about that, nothing I could apologize for. And then here's one of the slight disasters where Tormol is a compound, and Norwegian has the same cheerful attitude to noun-noun compounds that German does, namely to put all of the workload on the reader and not tell you where those two words break up into two separate parts, like the more accommodating English language does, putting a space between the two. And so Tormol can either mean an excursion, just as a single word, unanalyzed, but tur and mol are also two words which can be broken up into the compound triptung. And we were really busy thinking hard about noun-noun compounds because they're all over the place in Norwegian. Most of the time it's right to break the bigger word up into smaller pieces. This is one of those where it's not right. And we didn't get that quite right. But this was an easy problem for the BNC, the British National Corpus smoothing, to solve. That was never going to happen. A triptung is not something you get tripping off of your tongue most of the time. Okay, so just to remind you of those 3 steps. We take a sentence like Bergens området er tett befolket befriendelig, which means something. Since you don't know Norwegian, you don't know exactly what that means. We take the semantic representation which Helga Duvik helpfully produced in the same formal notation that we used for the English grammar, namely this meaning representation language called minimal recursion semantics. It's one of a family of widely used flat semantic representations that are essentially just a grouping of a collection of elementary predications, a verb plus its arguments or a noun plus its determiner, the semantic representations of those, together with some fancy hooking up for scope representations, for modals and negation and other logical operators. I will give you even less information about MRSs here. I'll show you a few more examples of those. This minimal recursion semantics or MRS representation essentially says that there is an activity or a state of befolka underscore V tells me it's some kind of verbal meaning, some state of affairs, some event, which has some arguments and is constrained in terms of tense and person and number to some degree. And then there's an entity of Bergens området, some kind of named entity. There's a passive operation, and there's this adjective fremdeles and another modifier tet. From those pieces, we want to try and build something that I can generate an English sentence from. For the target semantic should look something like this, that befolket turns out to mean something like populate, or is populated, and we tore Bergen's området apart into a compound. It's the Bergen area. You can see that with these two nouns there. And there's these modifiers still and dense, which we have to somehow put together in some fashion. And so we here manually put our effort in this project into writing these transfer rules, creating the problem space for yet another statistical model, where we said, okay, I can turn befolket into populate. That's not hard. Any Norwegian English dictionary is going to give me that mapping trivially. So we built a large part of this transfer component automatically from existing online resources. That wasn't tricky. Bergen's området, we had to do a little more work on to turn that into Bergen and area. This is the predicate introduced by the noun area in English, which further indicates that it can occur with an of prepositional phrase. That area of New York, or an area of 50 square meters. Area is, in this sense, a two-place predicate. It's a relational noun. And that's worn on its sleeve in the name of the predicate, but it doesn't matter here. It's just the Bergen area that we're trying to get across. And then, again, this simple pairing of tet and dense is available straight from any online corpus. So we had grad students and undergraduates, and even one of the professors in the project, because he was entertained by this, writing these transfer rules, which are building on abstract types which carry most of the work. So I can focus here on this two-place relation, and this two-place relation are aligned perfectly in their subject and their direct object, except they have a different sense, a different name for the predicate, an English name instead of a Norwegian one. So that arg12v1, the one that befolket populate pair instantiated, does actually this additional work. It says, if you give me an argument 1 and an argument 2, the subject and the object, I'm going to keep those exact same relations in the new predication that I build. The event is going to be just the same. That's the arg0 for us, the inherent event, which is present or past or future. And the scopal machinery stays the same. So every two-place verb pairing, which comes out of the dictionary, gets this additional set of constraints smuggled in, which helps us build the syntax semantics interface underneath the machinery without the human having to worry about that. This is the kind of rule that gave the professor much more in the way of headaches, a couple more gray hairs. For one of those noun compounds like Bergen's området, which is decoupled into Bergen plus area, we had to build rather a lot of noisy machinery, because in English, Bergen is a named relation that has a quantifier the built into it, and there's a compound relating Bergen to area, a two-place relation with these two guys, and then there's finally the noun itself, area, which is this guy, I guess, whose predicate name we don't know, because it could have been the Bergen population, the Bergen mountain. That noun compound could have Bergen as its left member for any number of right members. So this is an awful lot of typing they have to do to get one classical pair of relations working. We promoted that into its own type, name, and rel. And so if you remember, all the human had to write was this thing. It said, give me Bergen's området, and I'll break it up into these two. And everything else about that machinery to make it ready for the generator to work came essentially automatically. So then we present that MRS that I showed you before, this guy. I present that to the generator, and as I bragged about, the grammar is uninterested in the direction. It's happy to go both directions. So from this representation, it goes to the lexicon, and it says, I found a verb lexical entry, a two-place transitive verb, which has this semantic predicate. And I found a noun Bergen, and I found an area, and a dense, and a populate. Still, I looked up those lexical entries, and then I put them into the parser's bag, and essentially shook it. This is a method which is cheerfully called in the generation literature the shake and bake approach. Because there was this terrible product sold in the U.S. for a while, where instead of cooking your dinner for your children at home, you could go to the store, buy a piece of chicken and some floury stuff, and put the chicken in the plastic bag and shake it like this, and then throw it into the oven, and something almost edible would come out the other side. The product was called shake and bake, and that's roughly what we're doing in generation, in the sense that we're pouring these lexical entries in, we shake them up, and see what comes out. And on a good day, what comes out is this nice, lovely chicken in the shape of an English syntax tree, where the Bergen area is still densely populated, just read off the leaves of that, that's the output string. That's the translation of that Norwegian sentence. For a sentence like this, that all happens in about, 50 or 100 milliseconds. That's not hard. It's the long sentences that really cost us a great deal of pain. After we did this on that small data sample of about 5,000 original Norwegian sentences, 15,000 English ones, we shifted to a larger scale, not enormously larger. We wanted to see how this method would scale up. The Norwegian government gave us a little bit of money to do that, just to kind of keep us from bothering them too much. We took websites, scraped about 400,000 words of English and 250,000 of Norwegian. We added the additional lexical entries for the Norwegian side. The English side already had a predictive mechanism based on part of speech, so I didn't have to manually add the lexical entries for the generator. And we saw at the outset, from our nice limited set of rules that had focused on that small domain, about 43% success, compared to, if you'll remember, about 60% success that we had when the vocabulary was all within domain. So it's clear that this is still to some degree brittle. We worked for 3 feverish months, actually not that feverish, adding some additional machinery, and we brought it back up to just about the same, within a percentage point of the success rate that we'd had on the smaller data. So there was some amount of additional work we had to do to go find better sources of pairings of predications from Norwegian and English, bigger thesauri, a larger lexicon, some better choices about the ranking among scarce alternatives. But it was possible to bring this to 60%, and we saw a very similar improvement curve during that 3 or 4 months. The more effort we put in, the better we got, and we always just ran out of time and money before we ran out of opportunities to further improve that system. Okay, so the outcomes. This is the long version of chapter 1 of the 3 chapters. We found that efficiency was efficient enough to translate this data set. It would take a few hours to do that, but we had lots of machines. It's very easily scalable across parallel structures. Oslo now has 5,000 CPUs they can devote to this problem, so I think we can do this whole thing in about 20 minutes to translate 100,000 or 200,000 words. That's nothing like as fast as the statistical methods, but it means that we could do this kind of a cycle on a daily basis. We could work for a while, hand it over to the machine, the next morning find out what the changes had been. It's not an optimal feedback loop, but perfectly acceptable for research, and for relatively static data, probably perfectly all right for applications as well. We had very high quality in terms of the accuracy. We had humans then come to that final output and judge the quality of the translation manually, rather than using our automated tenfold validation method. So we looked at every one of the sentences that was translated, and ended up with about 70% being good or nearly perfect, and another 10% being kind of okay, and then about 20% that are bad. So the quality was reasonably high. We did not compare that measure against a statistical approach, although that would be an important next benchmarking test to do to see how they would do. Importantly, we found that these statistical models did much better than we'd expected. So we were saved from having to do that kind of painful heuristic-driven selection of interpretations. We had enough data, even with this rather small population, to do a pretty good job of that statistics. Okay, now take a breath. Clean translation out of your minds. Let's talk about story number 2, which is an ongoing project. Also being done on the backs of the wealthy and patient Norwegian taxpayers. But now we're working on English rather than on Norwegian. For reasons that I will only attribute to the salesmanship of my colleagues in Oslo, they agreed to spend 3 or 4 years pouring money into analyzing the Wikipedia and other online sources. They're actually more interested in Facebook, which we're doing too, but I'll talk to you about Wikipedia. That's the place where we started. We are again using the same grammar, the one we were working on in this logon and that I've used for 5 or 6 other projects as well. The same semantic representation. We are interested in both what we can parse and in looking at that 10 or 20% residue that falls outside the scope of the current grammar, what we can actually do. There are also resource limits. There are errors in the original input that we have to contend with. And we're interested in potentially using this for information retrieval. Luckily, we don't have to do anything very practical. It is enough to see whether we can apply these methods, come up with something that we can measure on some dimensions to show that there is progress, that there's some forward steps being made in the development. You guys all know about Wikipedia because you're under 50. Well, most of you. The Wikipedia is big. It is, for linguists, about as big as we want to get. People working on grammar-based methods don't typically look at more than 1 billion words of text as their working corpus, although that is changing year by year. This is a collection of documents that changes fast. Even back in 2008, when we took a frozen version of the Wikipedia as the basis for our work, the machinery was changing 220,000 edits per day, and even the small sample we were staring at changed from under us from one day to the next before we decided to do the freezing. So it's a relatively dynamic object, and I don't have the number of words that are in the Wikipedia today, but it's maybe approaching an order of magnitude more than that. I don't actually know what its size is. It still grows very fast. Our strategy was, and is, we started with a tiny sample, 100 articles. That's about 200,000 words, so a little bit bigger than the training sample we used for that logon data set, but now a new domain, potentially different training data needed. We applied that same strategy for parsing and then disambiguating. I'll tell you a little bit about the disambiguation process in a moment for building the annotated data. And we used our same maximum entropy statistical model for doing the parse selection. This is a discriminative model. It works reasonably well. We can throw whatever features and properties we can think of that might help in distinguishing one analysis from another. We can throw that in and see if it works. We're still experimenting with the components of that ranking model. Then we parse the full Wikipedia, that is all billion words, with this version of the grammar and that statistical model, which we have trained on these first 200,000 words of text. And you can get that first version. It was built using the English grammar dated last spring. We've just this month, while I was up in Oslo last week, frozen a new version of the grammar, which of course is much better, because I worked on it for another year. It must be better. We're going to release a new version, so you might as well just wait if you haven't started doing anything with this one already. We announced this at LRAC last year. We've had maybe 10 people who found enough space on their disk to download the 100 gigabytes of compressed file data, which is the annotated results, where we've stored the one derivation tree, which the statistical model thought was most likely for each of the sentences in that corpus, and the semantics that goes with it. We are now doing some manual evaluation of the sample, and we're going to, as I say, do this repetition. We found some systematic places where the grammar was just falling short. There were certain constructions. One of the most annoying was that hadn't come up in these other data sets very much. In English, you can say, some guy just walked into the room who I had never met, where who I had never met isn't modifying the noun it's right next to like any good relative clause should. It's modifying a noun off in the subject. A guy who walked into the room, right? Some guy walked into the room who I had never met. That who is not located with the man. And I'm very happy with unbounded dependencies that go to the beginning of the sentence, like WH questions, topicalization, all the good first-class citizens of unbounded dependencies. But this rightward movement was really annoying, and I hadn't put that in the grammar. I got away with that for quite a few years. In the Wikipedia, there seems to be almost a law against putting a relative clause next to the noun it's supposed to be at. They're all drifting off to the right somewhere. So a huge number of example sentences just weren't getting a parse, because if the sentence wasn't lucky enough to end in a word which could be a noun right before that relative clause, I came up with nothing. I wasn't getting the right analysis anyway, but I came up without anything at all. So that's one example. There's also phenomena. Are there linguists in the room? There might be some, besides the ones I know. Right node raising is also a phenomena. We spoke yesterday and discussed today with a colleague of ours. See if I can get it here. I sold John and... No, those are hard to do. Okay, off the fly I can't give you a clear, easy example of right node raising. I must be able to. John bought yesterday and sold today the ugliest little car I'd ever seen. So the buying was of the car, the selling of the car was of the car. Each of the verbs is modified by an adverb, but the single occurrence of that noun phrase is drifted off to the right again, where I don't like it to be, far away from the first locus inside that first verb phrase. So we had to deal with some of these phenomena. I've added a few of those, the most obvious ones. We're now going to see how well it works, and then manually measure the accuracy of that parse ranking model to see where we can improve that. And we're working on that unparsed residue, but that's sort of work I can't say much about because we haven't done a lot yet on that front. Just to remind you about this grammar, I said it was big, but big in terms of the lexicon. There are about 7,000 clusters of properties that make up the lexicon. Transitive verb is one little cluster, but it's made up of other clusters that share information within transitive verbs and ditransitive verbs. There are adjectives that behave a lot like transitive verbs or ditransitive verbs. There are expletive, subject, predicates. There's really more than you first think when you start subclassifying each of the major parts of speech into their component parts. And then there's a bunch of these that are annoyingly specific. So there is a type in this grammar for the pronoun me, which it shares with no other word in the language. There's another type for the pronoun I, shared with no other type in no other lexical entry in the language. These two words have one or two idiosyncratic properties that make them distinct from any other word in the English language. And since I'm doing everything by types, I'm forced to have some relatively specific types for these closed class entries. A rather surprising amount of that 7,000 types is to handle the frozen idiosyncratic part of the language in these closed class lexical entries. I've handwritten about 36,000 for the most common vocabulary, again driven by observations in the BNC. There are these 200 syntactic rules, which my friend Ivan Sog isn't very happy about. And then I've got a relatively modest inventory of morphological rules. If we were working in a real language like Czech, then, this would dominate everything else on the page, probably. But I took refuge in a rather simple language at this point. And you can see a demonstration of that grammar at your leisure at lingo.stanford.edu/ERG for English Resource Grammar. And you'll see the syntactic and semantic representations that we produce. Here's a couple of examples. This is the syntactic structure, and I guess this should look reasonably familiar. The lines aren't very clear in this projection, but you can see that there's a relative clause that we have studied modifying cats, and there's a relative clause modifying children down in here, and that's a direct object of the verb admire, which is the subject, and the subject of that verb phrase, don't admire, is this other noun phrase. That's completely vanilla. We think we're building about the same kind of syntactic structure that almost any reasonable linguist would accept as a candidate. Every linguist will change it slightly because that's why they're linguists. They find something new to say, but they would understand and expect I could probably defend that syntactic structure. The semantics that corresponds to that is this notation, which is a little bit hard to see. I've highlighted a couple of things in here. Oh, that coloring didn't work well at all. If you've got really good eyes, you can see the child is blue here and cat is red. And cat's red over here. You can see that each of these predicates plays a role in more than one predication. The point of this kind of representation is it's roughly a dependency-like structure. That is, I allow multiple occurrences in this representation where there was only one occurrence of the word in the original sentence. But I want to represent the different roles that the semantics of that word can play in the sentence. So there's a possession relation involving the dog and the child. There's an admiring relation involving the cat and the child. There's a studying relation involving the cat and some pronoun. Those are all pieces of what I can pull out of that particular sentence, that given the syntactic structure that we assigned using the grammar rules. Okay, so the area we chose, the data we chose for that corpus of manual annotation, I'll tell you a little about how we did that now, was the subpart of the Wikipedia that we thought we knew something about, namely computational linguistics. Well, it turns out there's a lot I don't know about computational linguistics. Computational humor was not my strongest suit, you'll be surprised to know. AOL by phone, we got rid of some of those. So there were some that came up that just didn't really seem, they had mentioned somehow computational linguistics, but they weren't very much fun. And we ended up with a nice round 100 articles representing just under 300,000 words. And here are some of the topics that we kept. So this corpus is also online. You can look at the annotated corpus. It's part of the Redwoods distribution, which I'll give you a pointer to a little later. If you work in the field of computational linguistics, you will recognize most of these names and not be too surprised by them. I was a little annoyed that companies like IBM and HP appeared in the top 100. But it's because they have spent hundreds of millions of dollars in research in NLP, so I guess they earned the right to have their names pop up in terms of frequency in this space. And of course, Blue, our good friend in machine translation, shows up. Here's an example of a sentence, again, just to remind you of the structure from the Wikipedia itself. Metonymy miscommunication is considered a primary mechanism of linguistic humor. A sentence I didn't have much trouble disambiguating, but it's not something I know a lot about. And here again is the dependency representation. You can see miscommunication showing up all over the place, the mechanism, metonyms, humor. These are the elementary predications we lifted out, which would be useful, we believe, for doing something like information retrieval. That is, I could build methods that would find these kinds of local collocations, even though they may not have been local in the original string. Here's a longer example. Computational linguistics is an interdisciplinary field dealing with the statistical and or rule-based modeling of natural language from a computational perspective. I showed you this because there's a little bit of the Wikipedia markup, the wiki markup that shows things being put in italics or boldface or something else. There's these alternate analyses. You can point to another link without actually having it be the word that shows up on the screen itself. And here I just splash a little bit of a diagram up there. You're not supposed to be able to read that even if your eyes are good. This is just a usual thing the syntactic structure says. By now you should get the idea that when I apply the grammar to a string of words, I'm going to impose one of those branching structures on the resulting string. And from that, or with that, I'm going to then compute a meaning representation. That's the meaning representation for that long sentence, and I only want to point out to you that there is an X18, the second argument of deal with, is something which is the nominalization of modeling. The sentence was deals with the modeling of natural language. So model is a verb turned into a noun. That's one of the non-branching rules in this structure, a category-changing rule. And then just to remind you that X18 has roles to play scattered around inside of the meaning representation. So we're always dealing with that as the kind of native representation, but recast often in terms of something more like a dependency structure. That's easier to deal with. It's easier to write programs for downstream. But I keep putting up this one because it's what the machine generates directly. Then to build the tree banking, finally, but what's supposed to be at the heart of the way we're doing the statistical approach, we parse using the grammar and using what is currently the fastest available parser. It's a C++ engine built by a guy named Ulrich Kollmeier, who now runs a company in Berlin doing grammar checking. We store up to 500 top-ranked trees. We always have a prior model because we've been working in this business for a number of years with other data sets. We always start with something. Using that pre-existing model, that prior model, I store the top 500 ranked trees. Then we present those to the humans, that is my underpaid undergraduate students, and also in Saarbrücken, and say, among these trees, find me the one that's the right one. Now, on the face of it, that's madness. I mean, nobody would do that even for the low pay that I give them at Stanford. But there is this nice mechanism, this insight that David Carter had way back in 1997, or that's when he published it, using a discriminant-based approach that says, for any sparse forest, I can divide the forest into two parts, those which either use a rule or a lexical entry or those that don't. They do or they don't. It's always binary. Either the rule was there, the lexical entry was there, or it wasn't. And it's straightforward to do that division so you produce the exhaustive list of all the possible ways that forest could have been broken up into discriminants. Was the report a noun or a verb? Was that prepositional phrase attached high or attached low? These kinds of differentiations. We present those discriminants to the students. They can make those choices, and then we have the power of two here coming to our benefit. They make a few choices, 4, 5, 6 choices, and they can identify the right tree out of those 500 trees with those local decisions. They're not making any global decision about the sentence. They have to have it in their mind, but they're making the local choices. And then we record that and hand that to a engine that does the parse selection, the statistical model that will be used to do the parse selection. I know you're going to have to go away, but don't wait on me. I'll just wrap this one up and then, yeah. Okay, so the success rate we've had in parsing that Wikipedia is just under 90%. Too bad. It'd be nice to be at the round number. So 9 out of 10 sentences we can parse. We can find a set of analyses, at least one analysis for that. Those are not all correct. So when let me show you the ambiguity in this case. The shape of this scatter plot is depressing. As the length of the sentence grows, even up to 10 or 20 words, I'm already at hundreds and hundreds of analyses. The trouble is that ambiguity is largely local, most often local. Every local choice I make in terms of the word choice selection or attachment selection creates another potentially independent source of ambiguity. And if you do 2 times 2 times 2 times 2 just a few times, you're up in the hundreds. It doesn't take much. If you have a 20 or 30 word sentence, the average length in the Wikipedia, there are lots of opportunities for binary ambiguity. So this is, on reflection, not a surprising property. You notice we cap it at 500. That's why there's that dark looming cloud at the top. I'm just not interested in counting above the 500 mark. It's clear we have a lot of work to do. There is a serious central problem in this ambiguity resolution. In terms of efficiency, we don't have anything to brag about. I just want to report the numbers to you. To find the first analysis takes us about 2 seconds, 2 CPU seconds on average, although that is wildly affected, of course, in a kind of exponential worst-case way by the length of the sentence. So up to about 20 words, I can get in under a second. But above that, it gets more expensive, and then you should hold on to your wallet because I'm capping the amount of resource I expend before. We allow hundreds of seconds, 180 seconds, CPU seconds potentially, before the machine's supposed to give up. That drives up this average rather a lot, but without very much benefit. I think I could probably cut that cost by a factor of 5 and lose almost nothing in terms of coverage. But here we're building the tree bank, so I want every possible ounce of ambiguity I can find. Here's the efficiency in a scatter plot, and you can see that shape of this curve is terrible once I get above 20. That's where the elbow hits, and beyond that, there's not a whole lot I can do to improve the efficiency, rather than starting to prune the search space, which we don't do. Okay, so then finally, to close this second chapter, and you'll be relieved to know the third one is a lot shorter, after we have done that manual disambiguation and built this completely manually annotated corpus, just over 80% of the sentences that were in the original 100 articles get a good analysis. We can find some analysis that is fodder then that we can use for the statistical model to train it to decide how to do parse ranking better the next time around. I put these other numbers up here to show you some of the other data sets we worked on in the past. Here's that MT Norwegian example where we had almost 90% survival. That is, 9 out of 10 sentences had a good analysis, but they were easier. The length of those sentences was less than it is for Wikipedia. And there are a few other domains we worked at. It turns out that online user forum data is not that much fun. And technical manuals are just terrible. They're badly written if you've ever tried to read one. Here's how you put your shelf together. Stand on your head and put one arm inside of your foot, and then make the pieces come together. Those manuals aren't models of good English accuracy, and our numbers here back that up. But we worked in various domains. This Wikipedia one seems like a promising one for us to use the statistical methods, and we can look at this on a much bigger scale, potentially acquiring rather more training data through some kind of automated self-learning, self-training approaches. To close then, though I've gone a bit over my time, let me tell you a little about what I'm currently being paid to do, which is to work on a grammar checking application for small children. And I'll go through this fairly quickly because the concept is a simple one. There are kids all over the United States who are trying to learn English grammar without very good materials and without very motivated teachers. And in a lot of school systems, they don't do very well at all against standardized tests. So we have a small study. We thought it was going to be small. It's now about 25,000 students in Memphis, Tennessee, who are using this software that I'm going to describe to you to see if they can improve their mastery of English. We do this by taking the same boring grammar I've talked to you about for an hour, used for machine translation and for Wikipedia, and we have now added some robustness rules, actually expanded the grammar with a handful of 10 or 15 rules that model the kinds of mistakes those students typically make based on data that we have available from a couple of years of prior use now. And then we used those robustness rules. If we had to employ them to analyze the sentence, then we have a message to give back to the student. I'll show you an example of that in a moment. The way the software works, we present a sentence or two of context, we ask the student a question, and then give them a little vocabulary that they can use to answer the question with. We tightly control that universe so we can maintain the precision and the clarity of the responses. And they get a second try, one try extra if they don't get it right the first time around. This did not project at all well. Sorry about that. I'll tell you what it says. There's some boring instructions that the students never read, so it's good if you don't either. And then the initial context is very simple here. Ricky stores his toys in his closet, and the question we ask the student to answer is, where are Ricky's toys? This is not a question about intelligence. This is just to see if they can use the grammar right. And they have a couple of verbs, are and be, some nouns, Ricky's desk closet, an article the, preposition in, a couple of pronouns, and a contraction Ricky's, like Ricky's going to the store, where it's Ricky apostrophe S for the B. And then they have a mouse that they can click on, and as they click on those words, they appear in this box down here, and they construct answers. And they do this in the tens of thousands. daunting. So from one snapshot we took from about a month of the students using the course, we had 865 attempts to answer this particular exercise. There are thousands of exercises in the course. And these are the good answers. Ricky's toys are in the closet was by far the most frequent. Ricky's toys are in his closet instead of the, pretty frequent as well. Nobody said the toys are in his closet. Apparently they don't like the pronoun here without the antecedent somewhere in. I'm sure a psycholinguist could explain that to me. But none of these are particularly weird sentences. It's a very simple example. Yet the distribution is wildly asymmetric. Here are the bad ones, which is what we're more interested in. The student would type, Ricky's toys are in closet, or Ricky's toys are his closet. The first one is grammatical, but wrong. The toys aren't the closet. They just left out the preposition. And here they got something which is semantically right, but they forgot to put the determiner in. The article is obligatory with count nouns in English. So our goal is to try and figure out what went wrong with the wrong sentences, reward them for getting the good ones, and do this all automatically in as little time as possible so we can give them responses. You might think we could just write down all the answers. Well, that's what they used to do until they hired me. For that short sentence, you can pretty much exhaustively enumerate the 50 or 60 possible right and wrong answers out of that small vocabulary. The combinatorics aren't terrible. When they started to move up in the grades, even to grade 5, these are students who are like 11 years old. They get a sentence like, why didn't Abigail want to go hiking after she'd been out and was tired? The answers could be anything like she was tired, too tired to go, didn't want to go hiking because she was tired. The students in 5th grade are supposed to be learning about these subordinating conjunctions. So they're supposed to use the word because. We don't force them to. But that creates the opportunity for 2 clauses. Each of those 2 clauses can vary exactly in the same dimension. She didn't want to go hiking because she was too tired to go hiking. She didn't want to because she was too tired to. I can vary the shape of that verb phrase independently in both places. This is one listing. Here's a few more. And I can give you 7 more pages just like this of typographically distinct sequences. So I pick one here. It's Abigail didn't want to go hiking because she was too tired to go hiking. Not particularly fluent, but perfectly grammatical. I would celebrate if I got that answer from the students. We don't so often. This is no longer fun for the grammar developer, the course developers to write down to enumerate. And it's highly error prone. They thought putting a grammar in place would be a good idea. So we've done this now for about a year. We have about almost 3 million answers that are in total, and of those, there are 1.4 million that were correct on the first try. That's pretty good. We were encouraged, although lots of the sentences are easy, and about 700,000 answers that were wrong. That is tokens, individual students who made an attempt. In terms of distinct answers, there were only about 12,000 correct ones, but you can see that the ways to get a thing wrong are much, much wider. There are so many ways to take a jumble of words and scramble them around and do some word salad, some shake and bake of their own, to create strings of words which are not English. And this is the real challenge. This is daunting, but could still be sort of done by the humans we have available. We don't pay the teachers very much either. But this is impossible. The numbers just explode, and as we add to the course, this becomes unsustainable. And then here's the other interesting number. These were the answers that appeared exactly once. Out of those 2.8 million sentences, students found ways of answering a question uniquely 2,000 times here, but 79,000 times in that incorrect answers. There's just a really large problem in dealing with that ungrammatical approach, a set of data. So our approach is to use the grammar, add these mal rules. We're stealing a very good idea that came from Schneider and McCoy back in 1998 out on the East Coast, to take a good grammar and make it a bad grammar or a more robust grammar by adding bad rules to it, rules for bad structures. We look for that presence of those rules, look it up in our error code table, and send some cheerful, scolding, encouraging message back to the student. One quick example. For that sentence, Ricky's toys are in closet, where they forgot the, we have a rule here that says take a noun closet, which is a singular count noun, ordinarily has to appear with an article, or a possessive, or something else, and turn it into a full noun phrase just as if it was a plural noun. So it's very similar to a fine rule in English for closets, which can be a full noun phrase on its own. We apply that rule and put a tag on it so we can discover it later once we present it to the engine for printing back the error messages, and we give back a reply to the student. We had to do 2 things to the grammar. We had to do those extensions, both rules like that very singular rule, and also lexical entries, because the student would write something like, Ricky likes go to the park. It should be, of course, Ricky likes to go to the park. We can't just tell the student verbs always have to have a to between them, because then the student would write, Ricky must to go to the park, which is not right. In English, the word must doesn't have the to. If they put must instead of likes, this would have been a great sentence. And it's understandable that students learning the language don't quite get that right every time. In this case, there's nothing funny about the syntactic structure per se. It's just that they have likes in the wrong category. They have it working like the verb must, when it's actually a different kind of verb, a more normal equi-control, subject control verb. But then we also decided we would reduce the grammar in some ways to remove ambiguity, which is just way annoying. If I allow the noun-noun compound rule, which is generic in English, we saw that earlier, I get all kinds of analyses. It's really hard to make sense of the kids' writing because they string words together, lots of nouns, and then put a verb at the end. And I could construct some kind of an analysis of that if I allowed any random noun-noun structure. So we've deliberately reduced this and imposed on ourselves the manual cost of licensing all of the multi-word noun constructions. That wasn't a good idea. I regret that now, but it's what we're doing. And then we also took out lexical entries that were just annoyingly ambiguous. No fifth grader is going to use the word flower as a verb. It pretty much shows up only in sentences like this. Art and science flowered in the 17th century. In a civilized city like Prague, you would use words like this more often. It doesn't happen in Memphis, Tennessee. And so there's no need for that verb flower to be present. It creates a kind of false ambiguity that just confuses the grammar. So we've done some customizing in both directions based on this one. Now, a couple more slides and then I'm done. The success in parsing here has to be extremely high. We have to be able to handle everything the students throw at us. We have to be able to say something, especially the good sentences. So the correct ones, we set ourselves a limit of no lower than 99%. One time in 100, I can fail to reward a student for a correct answer. That's challenging, but it's within range. These are not hard sentences. And remember, I control this group. I can control the vocabulary. If the grammar starts to have trouble with some construction, we can just move away from that construction. It's called cheating, but it's really good for building a big application that the students use. So this is not really a number you should put much confidence in. It just means I figured out how to game the system correctly to serve the larger goal of teaching these students grammar. And then in efficiency, again, these are not hard sentences. You remember that curve for efficiency kicked up at around 20 words. None of these students bother to click more than 14 or 15 times. They're done. They look for the next exercise. So these sentences are not long, and they fit well within the strength of the current parsing technology. On errors, we're currently saying something helpful about essentially 1 in 2 answers, incorrect answers the student gives us. If it's not correct, I either say nothing at all about it and tell them to try again, or 1 out of 2 times I actually find the right error, classify it correctly, and then give them a response. And in about 2% of those, I don't get it right. I guess wrong. I misanalyze the nature of the error that they made. That's acceptable. We will allow ourselves even about a 5% error rate. That's about what humans were doing before we turned it over to the machine. So the parse selection here is problematic because I'm using a parse selection model that was trained on hundreds of thousands of words of well-formed, largely well-formed text. And now I want to have these MEL rules sneak in here and compete. And I can't just do what would be the wonderful thing of a pipeline model. Give me all the good analyses. If you can't find any, then turn on those MEL rules. Because an example like this, she told the boy read a story, is ungrammatical in the intended reading, but it has another sense of she told the boy who was read a story. Easier to see if I gave you the sentence, she told the boy given a book. Namely, the boy who was given a book was told something. That's a grammatical string. The parser is going to find that analysis. If I say, only give me an ungrammatical reading or a report, if you can't find a good one, I'd miss this kind of construction. And they appear rather more often than you would think. The grammar is pretty creative at trying to find analyses. So we're now adding a tree bank customized for this domain where we parse and tree bank discriminate even with the ungrammatical rules folded in so that they get a chance to compete for results. Okay, final slide. We have found applications where we think the presence of the use of a linguistically informed grammar, together with the statistical parse selection to solve the ambiguity or partially solve the ambiguity problem, can actually serve a useful purpose. We know that these broad grammars create the ambiguity. That's just inherent in the approach we're taking to language. We use statistical models because we don't have the technology, the resources to do it manually. And we found that in these three areas we can demonstrate interesting benefits that come from the combination of those two resources. Thank you for your patience.
Okay, so thank you for the lecture and for the three applications. I am sure there are people who have done at least one of those three. So I hope there will be questions.
Good. Yeah, I'm happy for questions.
So thanks again for the very nice talk, and I believe we all have here some weakness for the deep and rich analysis. So my question was concerned about the coverage and the confirmed coverage in one of the slides previously, and
it's the slide that took me the longest to make, so I should put it back up again. That one.
Verified coverage.
Yeah.
So if I understand the labels correctly, the verified coverage is when the parser returned many analyses, and at least one of those was also confirmed by humans to be the correct one for the sentence.
Yeah, exactly.
And now the sad point comes. We see that you miss about 11% from the total to get to the observed coverage. So about 11% of sentences you are not able to parse.
Right.
Humans probably understand these sentences.
Sure.
There may be some grammatical errors, so part of those are for the inappropriate input, and part of those are the missing coverage of your system. But the 9%, the further 9% are an issue. So could you comment on it? Because the hope or belief would be that rule-based and deep grammatical approaches would be able to distinguish correct sentences and incorrect sentences, and in 9% they can't.
But remember, in the Wikipedia, almost everything is a correct sentence. There are very few actual errors there. And so this sad 9% loss here is where the grammar may or may not have been able to find that particular analysis, but it found some other analysis. So this is something closer to a true report of how much of the data actually is modeled by the grammar correctly. So if there is a construction like that extraposed relative clause, a guy walked in who I had never met, before I had that rule in place, for most of the sentences that included that phenomenon, I could find some analysis. It just wasn't the right one. Likewise for that right node raising case with the two verb phrases and the direct object off to the right that was supposed to be in both. There's very often an analysis where I ignore the fact that it should have been part of the first verb phrase, make that an intransitive verb phrase, and then build the second verb phrase so that there's a conjunction of two VPs. It's the wrong reading, but it's a perfectly fine syntactic structure. And so in those cases, I'm getting a false sense of optimism by saying, I got 9 out of 10 sentences under control. It was not the case. That sequence of words allowed me to think that I found a good analysis, but I'd either picked the wrong part of speech or a wrong attachment or some strange coordination, which gave me an illusion of coverage. This illusion of coverage is all you get from pretty much everyone out there who reports numbers on parsing. People typically don't report, maybe with the exception of people in this room, people don't typically report on whether it is the right analysis, because there isn't the basis for that measure. They can say, well, looks like the Penn tree bank. Looks a lot like the Penn tree bank structure. But they typically report measures at the local tree level, not at the full sentence level. This is reporting that every single iota, every punctuation mark, every letter in that sentence was exactly where it should be. As soon as there was one mistake, it drops from this category into this one or off the table. It just doesn't appear. So I think that's not quite the whole story. In this 80%, this loss of 9%, there are also sentences which I probably could cover, but where the parse ranking model was wrong. It dispreferred the one right reading because let's say that was a construction that appeared rarely. The machine found some other much more popular structure, which was just not the right one, and gave me 500 analyses that exploited that choice rather than the other one. So this is maybe a better measure, something like a better measure of the amount of work to be done. Now let me say one thing to reassure you about that gap. Part of the reason I'm in Saarbrücken this month is because there's a clever guy there named Yi Zhang who has been building a PCFG model using the same grammar, using the same annotated data. In fact, now using all of that Wikipedia data, billion words of annotated data with lots of mistakes in it. He builds a statistical, a PCFG model, that's a generative model, and from that he can, using standard techniques now available in the community, give me an analysis for every string of words he sees. So he can tell me something about the 10%, 11% that's missing here, and he can potentially also tell me something about this if I could assign some confidence measure that said, I don't think any of my analyses are right. Then we could fall back to that PCFG and get an approximate analysis, which we now think we can also compute a semantic representation for. Because that structure will differ from the one the grammar would have given us only in a couple of respects. Typically the grammar can do almost everything in almost every sentence. It just finds certain obstacles, barriers to success somewhere in that 20 or 30 word string. And so we think we now have a hope for saying reasonably interesting things about that remaining 19%, which are still linguistically informed, but back off in a sort of gentle way from the full analysis. I won't answer every question that wordily. But it's one central to my worries at this point, that issue about how we distinguish what the grammar can really do from what it, from on the surface of it, looks like it does.
So, unless there are other people who would like to ask
a follow-up question, yeah.
A clarification one first. The verified coverage is based on the single best output after the parse selection, or is it based on the human would scan on average 19 and a half items per sentence?
No, they're actually typically looking at 500 choices.
Okay.
So this is the number of tokens in the string. So this just tells you that the sentence length.
Sorry, number of items. Yeah. So the humans that confirmed the coverage actually read the 11,000.
Correct. Went through each of these 11,000 sentences, asked the parser to present the 500 analyses grouped by these discriminants, these binary discriminants. So the machine said to them, did you want the noun report or the verb report? Did you want high attachment for that clause or low attachment for the clause? Is that a relative clause or a complement clause? Each of those choices they would make. And in the space of typically now about 1 minute per item, they can arrive at a correct tree if there is one, or a rejection of all of the trees if there's no good tree. And so this takes lots of hours. This represents, I guess, about 1,000 hours or 500 hours of work to produce that. But the result here is an inventory of sentences for which in that 500 there is some right tree. Very often not the highest ranked one.
I'm trying to relate this to the figures that we know here, and if one uses a statistical parser and then say dependency one, and we have a tree-bank data for that, we can compare that directly. So the sentence accuracy, sentence level accuracy is around 30%. Am I correct? So this 80 looks much better than this, than the 30, but it's not the first best.
Exactly. The first best one is between 37 and 44% right now on the Wikipedia data. If we just turn it loose and do a tenfold cross-validation, train on 90%, test on the other 10%, we're getting under 50%, in fact hovering around 40% exact match for the first parse. So that sounds like it's in the same neighborhood. And our domain may be a little bit simpler, a little more coherent, because it's just this computational linguistics domain. The challenge of getting that exact match parse up above 50 or 60% seems awesome. I mean, that's a serious challenge. I don't think we mind very much. We've also now started also reporting the elementary dependency match. That is, these local pieces of that MRS. And that's typically around 85 or 88%, which looks more comparable to sort of standard measures out there for dependency matching. Yeah. Good. So I'm reassured that you're also not seeing much higher exact match than we are. Although I can certainly learn from how you're doing it anyway.
And one more question. There was an interesting chart. That was the ambiguity as the sentence length grows.
That depressing chart, yeah.
But the beginning is interesting. How come that? Was it this one? There was another one, and that was much flatter.
That's not ambiguity. That was just speed.
Okay, so that was
the efficiency one. Let me find it. This one.
This one. So the sparse time.
This one. Yeah. So this says that sentences up to about length 20 I can do in about a second. Under a second. The rate of growth of the ambiguity is squished down by the statistical model successfully, so that I can, and typically here I should also say, when we build a packed forest, we're using this packing approach to parsing like one should, and then we only unpack until we found the first 500. If the model is really good, I build that pack structure, we unpack only partially, we call it selective unpacking, guaranteed to produce the most likely outputs first. That's a clever algorithm. And in that case, if the model is well suited to the data, I can unpack very quickly and find all the 500 I want and stop and go on to the next sentence. This is the place where the unpacking is unsuccessful. I'm exploring much more of that space, and to unpack everything in that forest, that's expensive. That takes a long, long time. Even with the tight constraints the grammar imposes, that's a hard thing to do. And then it's also the case that there are just more chances of explosive ambiguity, a word that can be 5 ways ambiguous, or an attachment that can go 6 or 7 different ways. If somebody gives me a noun compound, I'm building every possible structure there, which is silly, but it's why I'm doing this bottom-up parsing. So there are local regions where I can get unlucky and see an explosion of ambiguity, and those explosions sort of drive me up into the upper atmosphere here, inevitably as the sentence length gets longer. Yeah.
So apart from the language model that helps you, could you relate that to the linguistic phenomena in the sentence? For example, if a sentence has 2 verbs, then there is say higher chance for the explosive ambiguity.
I have broken my head against that question for quite a long time now to see if I can identify, just by looking at a sentence, if I can develop the skill to say that one's going to be expensive. And what I do know is that if I see a gerund, something with a walking, jumping, singing, arranging, things start to go bad. Because those can be verbs or nouns, they can be modifiers, they can be predicative constructions, depictives. They have about 10 or 15 different distinct roles to play in a sentence potentially. And if I get 2 of those, then I start to see this disaster happen. So I could predict by looking at a sentence and counting the number of sequences of ing that occur, and I would know I'm going to be in trouble if there's more than one of those. But for lots of other sentences, it's like there's evil conspiracies in the grammar, where I take these 3 words which look innocent, but one of them happens to be usable as an adjective or a noun or a verb, and the next one also has that same ambiguity. And as soon as I get 2 or 3 words which are kind of amorphous about their proper category, the grammar starts to get creative about how it puts those pieces together. So there is a kind of a local opportunity for explosion, which I guess we could probably diagnose with part-of-speech tagger predictors. The one optimistic thing I can say about that problem is that in Oslo there is an expert on super tagging, the kind of thing that the Clark and Kerr and CCG grammars have to use in order to make things work at all. And we're just now applying that to see whether we can reduce at least the lexical ambiguity, which, as I told you, is the source of most of the information in the grammar. If I can do some super tagging to do a clever removal of the adjective for that lexical entry and the noun for that entry, I can at least delay the elbow of this curve. I can't eliminate it altogether, but if I can push it out to 40 words, I'm good, because most sentences of English don't come in that range. And so what we're hoping is that the super tagging can use a kind of a bulldozer to shove that whole thing out to about here, giving us essentially a linear factor of 2 in the word length without costing us more parsing. Then I think we're in really good shape. And I'm optimistic about that. It has a little cost in accuracy. Of course, I'm deciding early to do something that I might have to decide later. But with that early decision, I don't lose much accuracy and I get much, much better efficiency. Just for form's sake, someone else should ask a question. But you've been very patient. Anyway.
I just have a more technical question. Do you have, for some of the sentences, I assume, when you talk about the information extraction, you have the MRS structures.
Yes.
So do you have any corpus where you would have kind of manually checked the MRSs and could actually provide this type of deep analysis for the, for some sizable amount of data?
Yeah, you are right to be, from the fact that I've said little, to be skeptical that the semantic structures are well formed, because you can well imagine that there are few humans who are willing to take money to evaluate, going the other direction, to evaluate one of these semantic structures that I put up. There's one. So to look at that and say, oh, no, that's not right, this should be an X37 here, that's just not practical. Nobody's going to do that. What we have done, though, is provide use some existing mechanisms. There's a nice piece of software called uTool, produced by Alexander Kohler and Stefan Tatter in Saarbrücken when they were both there, that essentially studies the scope tree of this representation to see whether there's any gaps, whether there's any missing links. That is, they make sure that this is a fully connected graph. That is the biggest potential source of a failure in this case. The local dependencies are almost forced to be right if the lexical entry is correct, and over time we have investigated each of the 700 or 800 lexical types. The instances can't create trouble because they are just instantiating a type with an orthography and a semantic predicate name. So once I have debugged those 900 types carefully enough, they can't really fail to do the local construction right. There are weird cases where a new rule might fail to do something properly. But for the most part, I'd be prepared to say that the semantic quality is much, much higher than the syntactic quality, in that if out of those 80% that actually get a good analysis, I would bet good money that semantics is almost entirely correct. And it's partly because we've adopted this relatively rigorous semantic algebra strategy that Copestake and Laskarides and I developed in a paper a while ago that says for every grammar rule you're only allowed to do these basic operations, and she has a checker which warns me in rather noisy ways if I violate that coherence, that well-formedness piece with each syntactic construction and its semantic composition that goes with it. So we have built into the software the kind of checking devices which we think will save us from having to do the hopeless task of manually validating these structures. But it would be nice to have an end-to-end application that would do that kind of independent verification, like machine translation or something of the sort, or information retrieval. I'm getting bug reports from people building applications using the grammar in sort of little research projects, and they find occasional ones, but the fact that they're silent for days or weeks at a time makes me think that's not the biggest flaw in this resource.
Whether the sentence that we generated with only the same meaning with respect to particle or phrase.
Yeah, but then I'm testing two things at once. One is the generator ranking mechanism, and one is the generator itself. So an obvious flaw we would catch, but the machine can generate about as many strings as it can parse. I mean, as it finds analyses for. That is hundreds per sentence. So I'd need to find some way to get a reasonably good ranker with the top 5 or 10 and say, can you find a good one among these, and can you figure out why it did the others? But it sort of makes the brain hurt to look at those odd generated strings. But it does turn out to be a good sanity check. I always generate our standard test suite and see whether any sentences in that one sort of stand out as being weird. I don't quite know how to turn that into a kind of closed loop, because we would have to have a way of successfully selecting for new sentences exactly the right interpretation. But yeah, it's a benefit we have in this bidirectional mechanism.
This might be more of a comment. So actually you are saying that there is a very strong relation between the syntactic analysis and the semantic one, which normally I would say that people would say that for any given syntactic structure there might be tons of semantic analysis, and only one of them is usually the correct one, right?
Yeah, we have a much tighter view here. So we use an underspecified representation for the semantics to handle some of that ambiguity. So scope ambiguity of quantifiers, we don't represent at all. We simply leave it underdetermined. Every dog chased some cat is simply a single syntactic structure and a single semantic structure, which can then be scope resolved to either of the two, the wide scope or narrow scope for the universal. But for almost everything else, for PP attachment, noun-noun compounds, coordination, we commit ourselves in the syntactic structure to just one of the semantic readings, which is part of why our ambiguity is so ridiculously high, because we are maintaining this one-to-one link between the syntactic structure and its semantics. They are built at the very same time at the same unification step. When I combine two constituents to make a bigger one, I check the syntactic information and I compute the semantics all in one move. So there is it's a kind of non-standard approach there. We don't build the tree first and then project the semantics on top of it. They are part of this. It's part of the HPSG view of the universe, that these two things must be done in lockstep. They're mutual constraints on the same linguistic sign. Yeah, that may take a little getting used to think about that.
Any other questions? Okay, well, if there are no questions, so thank you once again very much for the talk, and I hope that if you want to talk to Dan, we have people subscribed for tomorrow, and then so you will be busy tomorrow morning, and I will talk more about that to you. And if you have questions, I think you might still be here for a second here.
Sure, yeah, I'm around for a while this afternoon, and I also have some time tomorrow afternoon as well. I'm not going away till the next day, so.
Okay, so if anyone, just you can write an email and make an appointment.
Yeah, and if you want to write to me directly, I'm danf@stanford.edu. Not so hard to remember.
Okay, thank you.
Thanks.
Thank you.